Okay, hello everyone. My name is Robert Alex, and I'll be presenting my implementation and analysis of the research paper Face Aging Simulation with Deep Convolutional Generative Adversarial Networks. This project and implementation was very challenging, as you'll see, but also very thorough and rewarding. I think I produced some pretty cool and interesting results, so I'm excited to share them, and let's get straight into it. Okay, so a refresher on the Face Aging Simulation with Deep Convolutional Generative Adversarial Networks paper. I think a quick review will help to remind everyone what goals I was trying to accomplish and how the original research paper set about doing them. And what novel ideas they brought to the table. So, if you remember, this paper proposed an improved face aging and de-aging model based on deep convolutional generative adversarial networks, or DCGANs, to generate stable and photorealistic face images while preserving personalized features and changing age conditions. The proposed model architecture consists of two subencoders, a generator and a discriminator. The two subencoders, EZ and EY, are used to encode and separate the personality and age features of input facial images. An image age discriminator, or I'm sorry, an age discriminator is added to the age encoder to learn age features accurately. These features are then input into the generator, which produces the corresponding aged face image, while the discriminator distinguishes between the input and generated images. So the real novel part of this architecture is the dual encoder split method used to preserve similarity features while also being able to gather the latent age features from the image, hopefully making aging easier. The authors also introduced perceptual similarity loss, which replaces adversarial loss as the objective function in the GAN. This loss is based on image features extracted from an intermediate layer of the discriminator, which is not shown here in the architecture model taken from this paper, a bit annoyingly. But we'll talk more about the objective functions later. In summary, you should know that the paper introduces a novel way of aging faces with with a dual encoder setup and perceptual similarity loss instead of just traditional adversarial loss. I'll start by saying that I implemented my model and training as closely as I could possibly decipher from the paper. There are newer methods out there on the internet that would probably improve, perhaps significantly, on this model, but I did not use them as I didn't think that was the point of the assignment. I tried to stay as true and possible to the architecture implementation described in the paper, which admittedly did not offer much detail describing their implementation outside of a few short sentences. So this left a lot of flexibility up to me, which ended up being a double-edged sword, as the paper is only 3 pages long, with pictures and references. So I would have appreciated more insight into how they accomplished their design and what parameters they used. Um, so I'll get right out of the way with it and say, unfortunately, my image creation was not able to match the standards of the image creation shown by the research paper. As you'll see, the model does create images that are similar to the original input image, but they're often convoluted, and training never seems to reach the high fidelity images shown in the original paper results. I will discuss reasons for why this may be later. However, that was only part of the assignment. The architecture also implemented the other half of the encoder structure, which is the age encoder and age discriminator. I was able to match the results from the paper on age estimation portion of the implementation. I'm pretty pleased about that, but I'll show the images and metrics later in the presentation after I describe my implementation in a little bit more detail. Okay, so how I did it. The paper seems to primarily use the Morph dataset, which is a large database with age labels that includes many instances of the same person at different ages. This seems like a very good dataset, and I would have loved to use it, but I was never granted access by the administrators that hold the rights to it. So I then switched to using the wiki-cleaned dataset, which is a database of images from Wikipedia with the subject's ages tied to it. I tested my first draft of implementation using this dataset, but after I did some debugging, I found that the dataset, even though it's advertised as cleaned, it still contains many errors and artifacts on both both the image and the age side. So I eventually switched to using the CACD cross-age celebrity dataset for the remainder of my training. This dataset is cleaner, although it's a bit harder to load and use in Google Colab. I still use the WikiClean dataset to do my age encoder testing and train after training on the CACD dataset. The paper uses 8 age categories. I ended up using 6. I thought I'd expand it to 8, but I never got around to it. Theoretically, it would be pretty easy change, and it should still work the same way. But I spent so much time focusing on trying to get the image portion of the project correct that I never changed it back to the 8 categories shown in the paper. The 6 categories are split from less than 18, then 30, then 40, then 50, then 60, then greater than 60. The ages are stored in one-hot vectors, with the index being the age category. All images are resized to 64 by 64 color images, normalized in a range between -1 and 1. My load data function can accommodate loading both from the wiki and the CACD dataset. Also, for more information on my implementation, you can just consult the report with this project. It goes into more detail on just about every category in this presentation can fit. And if you need more detail than that, please feel free to go straight to the code. I think I did a pretty good job commenting on it, so it should be pretty readable. All right, so let's get into my DCGAN architecture implementation. Well, really the age conditional DCGAN architecture. As I said before, my models are implemented exactly as described in the paper, which is mostly just the architecture image here, because that's all I really have to go on. And even that image is not fully correct, as I'll speak to later. But I'm showing this image one last time to keep it fresh in your head as I walk through my implementation briefly. Okay, so I wanted to show screenshots of my implementation here for each part of the model. Obviously, they're pretty difficult to read, but I will give a summary about how each of them works. So as I said earlier, the encoder part of the model is split into two separate encoders for age and personality. The age encoder is used to find the age-specific features of the given input image. The outputs of these features will later be used in the age discriminator to help train the age encoder, and the outputs go to the generator to produce aged images. The personality encoder finds the latent personality vectors from the input image and puts them into the generator to maintain similarity to the original image. So the generator does not ever see the input image at all. It only gets the outputs from the age encoder and the personality encoder. Okay, so the latent personality features EZ and age features EY are sent to the generator to produce images with the given personality at that age. Again, the paper gives no detail on how these models should be set up. I tried a whole bunch of different model architectures and kind of ended up with these because they seem to work best and they made sense to me. In fact, the paper does at one point say their model architecture is based off the quote, the implementation of the DC GAN, then gives a reference number 17 in the appendix, but the appendix 17 is not a DC GAN implementation. It's a link to an open source facial recognition software DILB. So I wish they had included that reference properly. I probably could have gathered some of the insights and answered some of the questions that I've been having regarding lack of information. Anyway, the discriminator of course takes in real images and the generated images and discriminates between the two. This is used to train the generator, and the generator trains the discriminator in typical GAN fashion. Shown in the discriminator here, I have included both the extraction of the intermediate features used in the eventual feature loss functionality um, and input age data as conditional information to the discriminator. Neither of these add-on additions are seen in the model architecture shown earlier, but they are briefly mentioned in passing in a later paragraph in the report, so I did add them in. Oh yeah, and we have the age discriminator that takes in real age labels and age predictions from the age encoder and discriminates between the two. This is used to train the age encoder. My results with the model are actually pretty good here, as you'll later see, which is counterintuitive since the paper provides very few details on how this relationship is supposed to train and work. Okay, so here are the loss functions again as a refresher. I already presented a lot on this topic during my in-class presentation, so I'll be brief here. My loss functions are implemented in the code exactly as described here for good or for worse, as I'll explain later. These are used in my train step functions, or in my train step function, which you're about to see, which takes in the images and real ages as one-hot encoded vectors and computes the loss functions, updates the gradients, and actually, trains the model. So again, for a better look at this, please review my code. It's difficult to capture the entire train function and multiple loss calculations all in one slide here. But in accordance with the loss function shown earlier, I use the reduce sum for most of the calculations here, which is kind of not considered best practice. Reduce mean is usually used, which averages over the batch size. I tried it with both, and the generated results were, for the most part, the same predictably, but it did make a difference, or it did make it difficult to visualize the resulting metrics, as you'll later see. So no real performance hit by staying true to the paper, but visualization of losses would have looked nicer if I used the mean function. Anyway, the train step function implements all the loss calculations from the previous slide. I tried dozens of different combinations in here to improve image generation and stabilization, but I could never find the fix that would solve all my problems. That being said, it does produce reasonable images, as you're about to see. I did play around extensively with the lambda values in my final LEG loss function. I tried to weigh it heavily to favor feature loss, as this seems to be the main issue with my image generation, but the weights never end up making enough difference to stabilize my image generation. All right, 11. Finally, the training loop. Nothing really special here. This just iterates over a user-defined number of epochs. I use 60 for all my final training since that's what the paper used. After it gets the loss results, it then updates a progress bar and tracks metric calculations. I also outputted the data to a data.csv file so that you have all the loss info for each epoch at the end. I use the CSV data for my loss visualization. Alright, and here we go. Here are the resulting images. As you can see, the images do maintain a resemblance towards the original input image subject, which is good and means that my personality, encoder, and generator are at least picking up on some of the right things. But the training process never converges enough to produce high-fidelity images that are shown in the paper. You can see the progress made over the epochs here. It starts out very fuzzy, then slowly adds more detail into the image, but then nearing the end of the training, this weird artifacting gets added and the image is never clearly showed. The colors and face seemingly underneath the fuzz in Epoch 60 do look more concrete, but the weird swirly artifacting prevent you from seeing the image clearly. I tried it with more epochs and that didn't make a difference. It just never converges. So the final result here of training, this is me with input to be aged to each age category. So in the first image I'm supposed to be less than 18. In the last image I'm supposed to be over 60. As you can see, the artifacting in the image prevents us from really seeing if that functionality is working properly, since the age features are pretty subtle and sometimes difficult to pick up on even in the original paper implementation results. However, if you swap back and forth between image 1 and 6, there are actually some differences between the images, which means the generator is distinguishing between the input age features. And if I'm being completely honest, I think that the image 6 does look a slight bit older if you swap back and forth. It may just be my eyes and brain telling me what I want to see, and it could be the fact that I'm a little delirious from lack of sleep over the past 10 days, but I have observed this behavior over multiple runs, so I'm led to believe that the aging functionality may actually be working in theory, but the messy images generated make it nearly impossible to tell. I know it's very difficult to see here, but I'm not making that up, I promise. You can see it if you swap back and forth quickly. Alright, so some metrics. I'm going to be quick with these as the reduced sum skews the metrics into varying ranges that make it pretty impossible to put all the losses onto one graph. If I use reduce mean in the calculations, most functions can sit on one graph, with the losses being around the 2, 1, or 0.5 mark, which is usually what you see in loss functions. But again, this is not what the paper did, so I stayed true to the reduced sum. Discriminator loss goes down and evens out, this loss is very low compared to the generator, which gets very high before evening out. Based on my research, this behavior could be considered normal and expected, but regarding my image results and how high the generator loss numbers are, I'm going to say this is indicative of my generator failing to produce the valid images. If it was working correctly, the shape and a behavior could remain the same, but the numbers would be more in the similar range to what the discriminator shows. So here's the really broken part, mainly my feature loss. My feature loss is astronomically high, whether you use either the reduce sum or the reduce mean function, and the graph shape is not what you want to see when you're trying to learn to reduce the feature loss. Again, this is most likely due to the generator not producing images with similar features to the original images. The intermediate output of my discriminator is picking up on that, which causes this loss to be so high. It also explains why my discriminator loss is so low and the generator loss is so high. The pixel loss also has really high numbers here, but the shape and behavior is generally what I would expect to see in my implementation, and I believe it is probably working correctly and is most likely responsible for the similar backgrounds and overall similar image structure produced in the generated images. Okay, so the age encoder and discriminator loss. This loss function I wrote myself, so the loss numbers are more reasonable than what you'd expect to see. The age encoder and discriminator learn well, as shown in evidence here in this graphic, but also by the results of my testing. The paper claimed to have an age estimation accuracy of 93% on new test images. My implementation produced around 86%. I'm pretty proud of this. I'm pleased with the results. I think my results could have gotten even closer if I used more data. Input data seemed to have an effect on the results, which makes sense. And if I did not use the WikiClean data set in the test set, as I mentioned earlier, the WikiClean set seems to have a lot of misclassifications and errors in it, so a cleaner test set and more data probably would have resulted in pretty similar numbers to what the paper results showed. All right, and conclusion. I've already used a lot of time here, so I'm going to be quick. Obviously, I was not able to reproduce the aged image fidelity results shown in the paper. This is disappointing, but if I could continue to work on it, I'd focus on the feature loss aspect. Fixing this would certainly explain why my images are not as clear as they should be and why my generator loss is so high. The generator seems to be maxing out on image fidelity at the moment, but there are 1,000 more things I could try, and I still have so many ideas. I really do think that another week of work, I maybe could have been able to accomplish all the tasks I originally set out to do. This is a very complicated architecture with lots of variables that were pretty poorly defined in the original paper, so it was definitely much more difficult than I'd originally anticipated. But I've never had another assignment in all of grad school that challenged me like this and let me explore my own solution in this way. So while it was a real struggle and training the GAN did make me suffer, I really did enjoy the process, and I'm actually somewhat pleased with the results. I'm obviously disappointed that did not work fully, but I did my very best here, and my agent coder architecture works well, and the images are still interesting. So overall, I'm pleased. All right, so that's it. This is my final project of my master's degree. So thanks so much, and I really did enjoy this. This class was interesting. I felt like I got to work on a lot of real-world applicable slash leaning towards like cutting-edge projects that was cool and unique throughout my curriculum. So yeah, this was great. Thanks so much, and have a great summer.